Hello dear students, this is your Engineering Mathematics 3 lecture. Today's topic is differential equations reducible to LDE, linear differential equations with constant coefficients. This topic is from first unit, linear differential equations with constant coefficients. And, there are two special differential equations which are not linear differential equation with constant coefficients, but we can reduce these two particular differential equations to LD, means linear differential equations with constant coefficients. That first special particular differential equation is Cauchy's differential equation or homogeneous differential equation. Now, what is that Cauchy's differential equation? The differential equation of the type a naught x raised to n into dn y by dx raised to n plus a1 x raised to n minus 1 dn minus 1 y by dx raised to n minus 1 plus a2 x raised to n minus 2 into d raised to n minus 2y by dx raised to n minus 2 plus also up to a and y is equal to x. Means with every differential coefficient, means with every derivative term, there is a polynomial function, and the degree of that polynomial function is equal to the order of the differential coefficient present in that term. See, in first term, nth order derivative term is there, and with nth order derivative term dn y by dx is 10, there is a polynomial function of the same degree n, and constant coefficient is also there, a naught. In second term, the n minus 1th derivative term is there, dn minus 1 y by dx is 10 minus 1. This is n minus 1th derivative term. With that derivative term, there is a polynomial function of degree n minus 1. In third term, n minus 2 derivative term is there. With that derivative term, there is a polynomial function of degree n minus 2. And differential coefficient, constant coefficient is a2, and so on. Means in every term the derivative is present, and with that derivative term there is a polynomial function also, and the degree of polynomial function is equal to order of the differential coefficient present in the term. And in RHS there is a function of x. So this type of equation is called Cauchy's differential equation or homogeneous differential equation. Now it is not LDE, linear differential equations with constant coefficients, but we want the solution of this differential equation. And to find the solution of this differential equation, first we have to reduce it to LDE, then we can find its solution. Now, how to reduce this differential equation, Cauchy's differential equation, to LDE? That is the question. And using one particular substitution, you can reduce this LDE. You can reduce this Cauchy's equation to LDE. Now, what is that substitution? Substitution is put x is equal to e raised to z. X is equal to e raised to z. Then that is, it means that z is equal to log of x. Because if we shift this exponential function in LHS, then you will get a log function. Z is equal to log of x. If x is equal to e raised to z, then the substitution for x into dy by dx is equal to d into y. This capital D is nothing but d by dx derivative, d by dz derivative with respect to z, because we are replacing the variable x by e raised to z. So your function which is present in RHS, function of x, it will be going to convert in terms of z, because we are using the substitution here, x is equal to e raised to z. So this capital D is nothing but d by dz derivative with respect to z here. So because of this substitution, x is equal to e raised to z. The substitution is x into dy by dx is equal to d into y. X square into d2y by dx square is equal to d into d minus 1 into y. If third term is x cube into d cube y by dx cube, then its substitution is d into d minus 1 into d minus 2 into y. If fourth order derivative term is there, then substitution is d into d minus 1, d minus 2, d minus 3 into y, and so on, where d is equal to d by dz. This capital D is nothing but d by dz. So using this substitution, you can reduce the Cauchy's equation to LD. Now, one example, solve x square into d2y by dx square minus x into dy by dx plus 4y is equal to cos of log of x plus x into sine of log of x. This is the equation, given equation. We want the solution for this equation. Now you check whether it is LDE. If it is not LDE, then is it a Cauchy's equation? Now, one thing is clear that it is not LDE, linear differential equation with constant coefficients, because with derivative term, there is a polynomial function. With every derivative term, there is a polynomial function, and the order of the derivative is equal to degree of the polynomial present in every term. See, in first term, second order derivative term is there, d2y by dx square. With the same degree polynomial is there, x square, and constant coefficient is here 1. Middle term means second term, minus x into dy by dx. The first order derivative term is there. With that derivative term, there is a polynomial function of degree 1. And last term, third term, that derivative term is absent, so that polynomial is absent here. And in RHS, the function is there, cos of log of x plus x into sine of log of x. Now, this is clear that with every derivative term, there is a polynomial function. So given differential equation is Cauchy's equation. So you state here, given differential equation is Cauchy's differential equation. Now it is Cauchy's differential equation, so you know how to reduce it to LDE. The substitution is here, put x is equal to e raised to z. X is equal to e raised to z, so z is equal to log of x. And the substitution x into dy by dx is equal to d into y. X square into d2y by dx square is equal to d into d minus 1 into y, so on, where d is, capital D is d by dz. We are using this substitution here to reduce the given d to LDE. So that first term, x square into d2y by dx square, its value is d into d minus 1 into y. So you write here, first term, replace it by d into d minus 1, that y is here common. Middle term is x into dy by dx, so replace it by dy. So it is d into d minus 1 in minus d plus the constant term is 4y, so y is common. You write in bracket 4. So it is d into d minus 1 minus d plus 4, bracket complete, into y is equal to cos of log of x. Log of x is z. So in RHS, the term is cos of z plus x is equal to e raised to z. So replace that x by e raised to z here. Sine of log of x. Log of x is equal to z. So replace that log of x by z. So in RHS, the term is cos z plus cos z plus e raised to z into sine z. And now simplify the bracket term, d into d minus 1 minus d plus 4 as d square minus d plus 4 means d square minus 2d plus 4 into y is equal to cos z plus e raised to z into sine z. This is the simplified form. It is nothing but LD. It is in the form of LD now. Phi of d into y is equal to f of z. In RHS, there is a function of z now. In place of x, there is function of z. So it is nothing but LD. It is LD, and you know the solution for LD now. You state here the auxiliary equation. Auxiliary equation is d square minus 2d plus 4 is equal to 0. And so d is equal to 1 plus minus I under root 3. D square minus 2d plus 4, it is a quadratic equation, and you know how to find the factors for this quadratic equation. D square minus 2d plus 4 is equal to 0. Using the formula, where in first lecture we have discussed the formula to find the roots of quadratic equation. Using the formula, you find out the roots, and the roots are here. D is equal to 1 plus minus I under root 3. And this is these are the complex roots. There are two roots. They are complex roots. Alpha is 1 and beta is root 3. So the complementary function is here, e raised to z in bracket c1 cos root 3z plus c2 sin root 3z. This is the complementary function here. using the rule of complementary function. When the factors are complex factors, roots are complex, then how to write the complementary function for that complex roots. Using that formula rule, we have written here the complementary function. Okay, now the particular integral, it is equal to 1 upon d square minus 2d plus 4 in bracket cos z plus e raised to z into sin z. There are two different terms, so you separate both the terms like this. In next step, 1 upon d square minus 2d plus 4 into cos z plus 1 upon d square minus 2d plus 4 into e raised to z into sin z. So these are two separate terms. Now solve for cos function, cos z. You know how to solve for trigonometric functions, sorry, sine function or cos function. We always replace the term of d square by minus a square. A square, a is the coefficient of trigonometric function. Here function is cos function, and with the z, that angle z, the coefficient is 1 and the square of 1 is 1. So we replace d square by minus 1. We replace d square by minus 1, then the term in denominator will be minus 1 plus 4, 3, and this minus 2d as it is, because we are replacing only the terms of d square. So the in denominator the term is 3 minus 2d cos z plus. Now the second term is e raised to z into sin function is e raised to z into sin z. So here use case 5 or type 5 of shortcut method, because there is a product of two functions. One of them is exponential and second one is trigonometric function. So you replace the term of d, the term of d by d plus 1, because we are going to solve for exponential function first. So e raised to z as it is, the coefficient of e raised to z is 1. So replace the terms of d by d plus 1 in every term. So denominator is d plus 1 whole square minus 2 into d plus 1 plus 4 into sin z. Okay, now solve for exponential function first here. And now the first term denominator is 3 minus 2d and function is here cos z. Now how to solve for cos z? We always replace the terms of d square and not d. Now there is a term 3 minus 2d. So the term is, there is subtraction of two terms, so we cannot integrate cos z here. If there is a single function d in denominator, then in that case we can easily integrate. But here the term is 3 minus 2d. Then how to remove this d from denominator? Then multiply and divide the term by 3 plus 2d. 3 plus 2d, denominator 3 minus 2d into 3 plus 2d. 3 minus 2d into 3 plus 2d, the reduction will be 9 minus 4d square into cos z plus e raised to z. In second term, e raised to the work of e raised to z is over here. So e raised to z as it is. In denominator, expand the term d plus 1 whole square. So it is d square plus 2d plus 1 minus, solve this bracket term, minus 2d minus 2 plus 4 into sin z. So that first term now 3 plus 2d upon 9 minus 4d square into cos z. Now the trigonometric function cos function is there. So replace the term of d square by minus 1 like the second step. Now if we replace d square by minus 1, so it will be minus 4 into minus 1 plus 4. So 9 plus 4, 13. So in denominator the term is 13. Numerator the term is 3 plus 2d. Denominator 3 plus 2d upon 13 into cos z plus e raised to z. Its work is over, so it is as it is. Now simplify the denominator term, d square plus 2d plus minus 2d get cancelled. 4 plus 1, 5, 5 minus 2 is 3. So it is 1 upon d square plus 3 into sin z. Now the next step is, you solve 1 upon 13 is constant, so you take it as it is. Now solve this bracket term 3 plus 2d for cos z. 3 into cos z, 3 cos z, then plus 2 as it is. D of cos z, d means derivative. You know that capital D means derivative and 1 by d means integration. So capital D into cos z means derivative of cos z is minus sin z. That's why minus sign is here, minus sin z. This term is solved. Now the next term plus e raised to z as it is. Now solve for sine function, sin z. You know that how to solve for sine function. Replace the terms of d square by minus 1, because the coefficient of sine function is here 1. The angle is z, so the coefficient of z is 1. So the square of 1 is 1. So you replace d square by minus 1 using the second case of shortcut method, d square by minus 1. So if we replace d square by minus 1, so minus 1 plus 3 is 2. So it is e raised to z upon 2 into sine z. So this is pi, and so what is the general solution? Y is equal to CF plus pi. Y is equal to CF plus pi. So you just do the addition of complementary function plus particular integral. This is your answer for the Cauchy's equation, given Cauchy's equation. This is the second example. You try yourself. X square into d2y by dx square minus 4x dy by dx plus 6y is equal to x raised to 5. In this example also, with every derivative term, there is a polynomial function of the same degree. So given differential equation is Cauchy's equation. So you take it as a homework and you try to solve this example. Next equation which is reducible to LDE is Legendre's differential equation. This equation is we can reduce this equation to LDE. Now, how to reduce it? This Legendre's equation to LDE. First, see what is that Legendre's equation. The differential equation of the type a naught into x plus b to the power n into dny by dx raised to n plus a1 into x plus b to the power n minus 1 into dn minus 1 y by dx raised to n minus 1 plus up to a and y is equal to x is called Legendre's differential equation. See, with the derivative term, first term, nth order differential coefficient is there, dny by dx raised to n. With that derivative term, there is a polynomial function in the form of ax plus b and its degree is n. So with the derivative term, there is a polynomial function with the same degree and constant coefficient is also there in every term. So this type of equation is called Legendre's equation. See, second term, the n minus 1th derivative term is there. With that derivative term, there is a polynomial function of the type ax plus b, and the degree of the polynomial is equal to degree of the degree of the polynomial is equal to order of the differential coefficient present in the same term. So if this is the condition, then that type of equation is called Legendre's equation. In RHS, there is a usual function of x, like the LDE. Now, how to reduce this differential equation, Legendre's differential equation to LDE? There is standard substitution. Put ax plus b is equal to e raised to z. Now, if ax plus b is equal to e raised to z, then z is equal to log of ax plus b. Because if we shift this exponential function in LHS, then it will be a log function. So z is equal to log of x plus b. And how to reduce the term here? You just see ax plus b into dy by dx. Its replacement is a into dy by dz. A into dy by dz. It means ax plus b into dy by dx. Its replacement is a into dy. And similarly, ax plus b whole square into d2y by dx square is equal to a square into d minus 1 into y. Remember these substitutions only. Put ax plus b is equal to e raised to z. So that z is equal to log of x plus b. And how to replace the derivative terms? Ax plus b into dy by dx is equal to a into dy. Ax plus b whole square into d2y by dx square is equal to a square into d minus 1 into y. Next is x plus b whole cube into d cube y by dx cube is equal to a cube to d minus 1 into d minus 2 into y is y, and so on. Here in all the terms, that capital D is nothing but is d by dz, like Cauchy's equation. You remember here d is d by dz. So we are using the substitution x plus b is equal to e raised to z. Now the example here, solve 2x plus 1 whole square into d2y by dx square minus 2 into 2x plus 1 to dy by dx minus 12y is equal to 6x. We want the solution for this differential equation. So check first which equation is given, whether it is LDE or Cauchy's equation or Legendre's equation. So in first term, second order derivative term is there. With the second order derivative term, there is a polynomial function in the form of ax plus b, and the degree of the polynomial function is 2, which is equal to order of the derivative present in the same term. And the constant coefficient is 1 here. Middle term, the derivative term is dy by dx. With that derivative term, there is a polynomial function 2x plus 1, and its degree is 1 here. So the order of the derivative is equal to degree of the polynomial. In third term, the derivative is absent, so that polynomial function is also absent in the form of x, 2x plus 1. And in RHS, the function is there 6x. So you state here, given differential equation is Legendre's equation because it is in the form of x plus b to dny by dx plus 2n. Here, if we compare with x plus b, the value of a is 2 and the value of b is 1. So remember it. Now, how to reduce this differential equation, Legendre's equation, to LD? Substitution is put 2x plus 1 is equal to e raised to z, and so z is equal to log of 2x plus 1. Now you find the value of x from 2x plus 1 is equal to e raised to z. So x is equal to e raised to z minus 1 by 2. Here. So next substitution, 2x plus 1 into dy by dx is 2 into dy. 2 into dy because here the substitution is ax plus b into dy by dx. This substitution is a into dy. So in that particular example, the value of a is 2. So we are replacing it by 2 into dy. Then ax plus b whole square dy by dx square. Its replacement is a square into d minus 1 into y. So it will be 2 square d into d minus 1 into y. That example. See, 2x plus 1 into dy by dx. Its replacement is 2 into dy because the value of a is here 2. And 2x plus 1 whole square into d2y by dx square is 2 square. 2 square is 4. So you write here 4. 4 into d into d minus 1 into y, where d is d by dz. So that equation becomes 4, see, 2x plus 1 whole square into d2y by dx square. Its replacement is 4d into d minus 1. So write 4d into d minus 1 into y minus, middle term is, check here, middle term is minus 2 as it is, and the replacement of 2x plus 1 into dy by dx is here 2 dy. Its replacement here, see, 2x plus 1 into dy by dx. Its replacement is 2 into dy. So replace it by 2 into dy. Minus 2 is already there in example. Minus third term is minus 12y as it is equal to 6x. Now what is the 6 as it is? What is the value of x? We are going to convert that x in terms of z, because our substitution is here 2x plus 1 is equal to e raised to z. So x is equal to e raised to z minus 1 by 2. This is from the substitution. From this substitution, we have this calculation, x is equal to e raised to z minus 1 by 2. So 6x is equal to 6 into e raised to z minus 1 by 2. Now 2 3s are 6. So you simplify it. So it is in RHS, it is equal to 3 into e raised to z minus 1. Now in LHS, that every term contains multiple of 4. So we can take 4 common. Also y is common. So take it common. So 4 common. So remaining term d square minus d minus d. The 2 to the 4 is here a common. So y is also common. So middle term minus d only here. Minus 12, 4 3s are 12. 4 is common. So remaining term is 3. Bracket complete into y is equal to 3 into e raised to z minus 1. Now next term, that 4, you transfer this 4 in RHS. It is a multiple. It is in multiplication to the in LHS side. So if we transfer it, it will go to division. 3 in RHS, 3 by 4 into e raised to z minus 1. And in LHS, you solve the bracket term, d square minus d minus 2d. So d square minus 2d minus 3 into y is equal to 3 by 4 into e raised to z minus 1. Okay. So this is nothing but LDE. It is in the form of phi of d into y is equal to f of z. So you state which is LDE, and so here the auxiliary equation is d square minus 2d minus 3 is equal to 0 is an auxiliary equation. Now this auxiliary equation, its degree is 2. So you find out the factors. The factors are here d minus 3, d plus 1 is equal to 0, because minus 3 plus 1 addition is minus 2 and the multiplication is minus 3. So the factors are d minus 3, d plus 1 is equal to 0. And so d is equal to 3 and minus 1. These are the factors here. So complementary function, there are two factors, both are real numbers and they both are distinct. Distinct means different. So complementary function is there. c1 e raised to 3z plus c2 e raised to minus z. Okay. So what is particular integral? Particular integral is here 1 upon d square minus 2d minus 3 into 3 by 4 into e raised to z minus 1. 1 upon phi of d into f of z. 1 upon phi of d is here. This d square minus 2d minus 3, and your function f of z is here 3 by 4 into e raised to z minus 1. Now solve this pi. We find the pi, solve for the function. The simple exponential function. Separate one term contains exponential function and second term is a constant term. So use the first case of shortcut method, first type of shortcut method. Separate these two terms first. See the next step. 3 by 4, this term is constant, so write down as it is in bracket 1 upon d square minus 2d minus 3 into e raised to z minus 1 upon d square minus 2d minus 3. Okay, separate both the terms. It is equal to pi is equal to 3 by 4 as it is. Now how to solve for exponential function? The first case of shortcut method, we replace the term of d by the coefficient of exponential function. The coefficient of exponential function is here 1. The coefficient of z is 1 in exponential function. So replace the term of d by 1. So d square means 1 square. 1 square 1 minus 2. The value of d is 1. So middle term is also minus 2. 1 minus 2 minus 1 minus 1 minus 3 minus 4. So the term is minus 1 by 4 into e raised to z after replacing d by 1. Second term, in second term, the constant term is there. No function is there. The constant term is 1 is there. So if the constant term is there, then we use the special subcase of first case of shortcut method. We replace d by 0 if there is a constant term. So replace the terms of d by 0. D is equal to 0 in denominator. So only non-zero term is minus 3. Minus 3 and this minus sign plus. So the term is 1 by 3. And so the pi is 3 by 4 in bracket minus 1 by 4 into e raised to z plus 1 by 3. So this is the pi, and so the general solution is y is equal to cf plus pi. You write down cf, c1 e raised to 3z plus c2 e raised to minus z plus 3 by 4 in bracket minus 1 by 4 into e raised to z plus 1 by 3. Now your answer is y is equal to some function of z, but our original example is in the form of x and y. So your answer must be in terms of x and y. So the value of y, you replace the value of z. You know that z is equal to log of x or x is equal to e raised to z. So replace x by e raised to z. So the first term c1 e raised to 3z means 2x plus 1 whole cube plus c2 e raised to minus z means 1 upon e raised to z, and e raised to z is 2x plus 1. So in denominator the term is 2x plus 1 plus 3 by 4 in bracket minus 1 by 4 as it is. E raised to z means 2x plus 1, right here 2x plus 1 plus 1 by 3. So your answer is in terms of x and y. So this is the solution for Legendre's equation. This is Legendre. Say similarly, you have to replace the terms of z by the substitution, means in terms of x. In Cauchy's equation also, we have solved one example of Cauchy's equation. In that equation also, you have to replace in last. So you have replaced it. Y is equal to cf plus pi. So y is equal to cf. Every term is your solution is in terms of x and y. Means you in last you put your substitution. Means your answer must be in terms of x and y. You use x is equal to e raised to z, means z is equal to log of x to get your answer in terms of x and y. So this is the topic, equations reducible to LDE. We have discussed two particular differential equations, Cauchy's equations and Cauchy's equation and Legendre's equation. And so this topic is over here. Thank you.